So what happens when you actually run Python? It loads the source code of your file, it tokenizes it, it turns it into an abstract syntax tree. It then makes a control flow graph where it takes all the blocks in the syntax tree. This is the kind of Minecrafty bit. It puts them onto blocks and then looks for the flow of control through the blocks. And then finally it flattens it into bytecode. It's fully compiled as bytecode. And then the interpreter loop goes through the bytecodes and runs each statement. We're going to make a really simple file. We're going to do x equals 1. Really simple piece of source code. Now we have the text loaded as a string. So we want to split it up into its parts, and then we may also want to name its parts. X is a name, equals is an operation, and then 1 is a number. So there we've tokenized the file into its parts, and we've given some meaning to the parts. This is pretty much how it works in the Python interpreter, as I'll show you. So we import the tokenize module, which breaks a stream of bytes, like your raw source, into Python tokens. It generates 5 tuples with the following members: the token type, the token, the starting row indices, the ending row indices, and the original line. These tok are these named tuples, as we just saw. So we run this, and you see it has spitted out all the tokens. It started with a default string format declaration, Unicode, UTF-8. Then we have a new line, that new line there. Then we have the name def. Def is a name of a statement, and we have where it is and what line it's on. Then we have the name of the function, answer to life, universe, and everything. Then we have an open bracket, which is an operation. Then we have a closed bracket. Then we have a colon. Then we have the new line. Now the most important bit for Python is that we have the indent. So other languages like C and JavaScript, they open and close their functions with some ugly braces. But Python doesn't. But when it tokenizes the source, it basically does the same as C and JavaScript. It notices the indents and the de-indents. And then we have a name, the return statement. Then we have a number, 42. Then we have a new line. Then we have the de-indent, and then we have the end of the file. So that's pretty simple. That's pretty much how all programming languages do it, except for the indent and the de-indent. Okay, so what it does, it takes those tokens. That tokenize function is actually called by this AST parse function. So that's kind of like hidden inside AST parse. But it takes the source code, tokenizes it, and put it in what's called an abstract syntax tree. It's now turned those tokens into semantic meaning. Because of the def, it knows there's a function. And the name of the function is increment. It has no positional arguments, but it has one normal argument, which is x. Has no keyword argument, has no keyword defaults, there's no argument defaults. And then the body of the function. Now it's noticed the name return matches to a statement, which then is turned into this function here, return. And then the value of the return is a binary operation. Now a binary operation in Python abstract source tree means like a calculator operation, like plus, minus, divide, multiply. And then on the left side of that sum is x. Then the operation is add. And on the right is the constant value 1. So if we go to the process, we have source code, which is then turned into tokens, which is then turned into an abstract source tree. Then it does the compilation step. Python is written in blocks. You have blocks of code. You have functions, and you have if statements, and you have returns, and you have yields, and you have classes. The code is all in blocks. So the abstract syntax tree converts all those blocks into semantic meaning, into functions like this. And then the compiler makes the control flow graph, which then deals with all the branches and all the jumps. The branches like if and while and for, and the jumps, break, continue, return, raise, exception handlers, try, except, finally, functions. And then it basically reasons about the flow of control for all the blocks, and then flattens it into bytecode instructions, which it does loads of stuff that's too long to cover in this video, but it does like dead code elimination, like dropping any unreadable blocks. It works out the jump offsets, which we'll explain later, and it organizes like the scopes and the exception tables. Let's say we have code that looks like this. it will produce a load of bytecode instructions, to be explained shortly, for the first line, and then it will have a block for this line, and then it will have a block for this section. The control flow graph is like looking at how all the blocks and the edges work. So it turns it into bytecode. So let's look how it compiles. So if we have some simple functions, increment function, if a number is significant or not, a simple Python code, then we can produce the abstract syntax trees. So I'm printing out 2 here. So I have the first one for the increment. We did this already. And then the second one is for this slightly more complicated one that has branches in it. So we have a function definition. The def makes a function definition. And the name of the function is signum. And it has the argument x. It realizes there's an if, so it makes this if function. And then there's a test, which is a comparison. And on the left side is the name x, which it loads the value of. Then at the op is the greater than. The comparison here is the constant value 0. And then we have a return if that passes. Or else we then go to the next bit here. We have another if statement. On the left again is the x. We load the value. We then have the op, which is the less than comparison. And then we compare the value 0. And then if that passes, we return the reversed -1. So reverse it becomes -1. And then we have, or if it's not less than 0, it's not greater than 0, then it's 0, so we turn 0. We make the ASTs, and then we compile them. Let's do the simple increment one first. There we go. And now that's compiled that into the bytecode instructions here. Resume, which 0. Resume with an argument 0, which means that it's the start of the function. It's not returning from some other kind of construct like a yield or an async IO. Or it's loading the first value from the values table, which will be the value of x. It's loading the second constant it knows about, which is 1. The first constant I know about will be none, like N-O-N-E. It's doing the binary operation 0, which is the plus, and then it's returning the value. And now if we disassemble get the bytecode for the significant number one, the more complicated example. We resume 0 means we're starting, interesting name, but it means resume 0 is starting from scratch. It's on at the beginning anyway of the block. Then we're loading the first value in the values table, 0, which also happens to be 0, but index of 0. Then we load the constant 1, which is actually an index in the constants table. Then we do the compare operation, the greater than. Then we pop jump if false. Now with pop jump, we leapfrog over the relevant lines. So on line 3 of the function, if this is false, if x is greater than 0, we return the constant at the second of the index of the constants table. So if it's true, we carry on. But if it's false, we do a pop jump. We leapfrog. So we leapfrog one line, which gets us to here. If it's true, we do this. But if it's false, we leapfrog one line, and we go down to here. The bytecode actually does the false case first. So the false case, if it's false, we jump over this line and go to this line. We jump one line. We leapfrog, like our frogs there. We leapfrog one line. So if it's false, we leapfrog this line. If it's false, we leapfrog this line and go down to here. So if it's false, we leapfrog the return 1 and we carry on. But if it's true, we return, and that's the end of the game. But if it's false, we leapfrog the return statement. So we pop jump if false 1. So we leapfrog the return statement, and we're now at this elif. So now we load x again, and we load the first constant, which is 0, from the constants table. Then we have the same thing again. So pop jump if false. So if it's false, we pop one, we leapfrog one line. So we go from here to here. But if it's true, then we return the third constant. But if it's false and we've jumped over this line, we've jumped over this line, then we're onto this line and we return the constant. And that's the end of the program. Don't worry if you didn't understand any of that bytecode, because I'm going to explain it in more depth in the next video. But I just wanted to go through the whole process. We start off with source code. When we run it using Python, it tokenizes it. It turns into an abstract source tree. It compiles it. Then you get bytecode. And then the interpreter loop executes the bytecode. And it does all this in milliseconds.